And we're back in better than ever, still in 19-2, where we're talking about the hydrogen ions and acidity. In the first podcast of this section, we took a look at the autoionization of water, the equilibrium that exists within water, between water, the hydrogen ion, and the hydroxide ion, and talked about the fact that acidity and basicity is simply a comparison between the amount of acid ions, the hydrogen ions that are in the solution, and the amount of basic ions, the hydroxides that are in solution. So when you compare the two, you can determine whether or not a solution is acidic, basic, or neutral. And so we're working right now through the practice problems where we're calculating the amount of hydrogen and hydroxide concentrations and determine whether or not the solution is acidic, basic, or neutral. So letter C. Now, we have hydrogen equaling 2 times 10 to the negative 7 molar. So Kw equals the hydrogen ion, which is 2.0 times 10 to the negative 7, times the hydroxide ion, which is unknown at this point, and that's going to equal 1.0 times 10 to the negative 14. We have to divide the 2.0 times 10 to the negative 7 over to the other side, and now hydroxide is going to equal 1.0 times 10 to the negative 14 divided by the 2.0 times 10 to the negative 7. Of course, those had canceled out in the previous line. And when you perform that calculation, you get 5.0 times 10 to the negative 8 molar hydroxide. So now, once again, if you compare your acidic ion, which is 2 times 10 to the negative 7, you compare that to the basic ion, which is 5 times 10 to the negative 8. Which one's larger? Well, some people will confuse this and say that 5 is greater than 2 so that the hydroxide is larger, but again, you got to look at the powers of 10. This is 10 to the negative 8. This is 10 to the negative 7. This one is larger, so therefore the solution is acidic. The hydrogen ion concentration is greater. And finally, letter D, you have hydroxide is 1 times 10 to the negative 7 molar. You might already know this just by looking at it, but let's go ahead and do the calculation. Kw equals hydrogen times hydroxide, which is 1.0 times 10 to the negative 7. And that's going to equal 1.0 times 10 to the negative 14. We're going to divide both sides by the 1.0 times 10 to the negative 7. These divide out. The hydrogen is going to equal 1.0 times 10 to the negative 14 divided by 1.0 times 10 to the negative 7. And so in this case, the hydrogen equals 1.0 times 10 to the negative 7 molar. Compare the acidic ion to the basic ion, and if you notice, they're the same. So therefore, the solution is neutral. This is the same as this. The hydrogen is the same as the hydroxide. Okay? Alright, so if you want to determine if something is acidic, basic, or neutral, you have to compare those ions. But if you notice, that's a lot of number crunching, and the way you report it is a little bit cumbersome. So they developed a slightly more user-friendly way of reporting acidity in a solution, and that's the pH scale. All right, pH is simply equal to the negative log of the hydrogen concentration. That's a bracket. The negative log of the hydrogen concentration. Or, if you want to go back the opposite way, you can just take 10 to the negative pH, and that will tell you what the hydrogen concentration is. Now, just a quick review of logs. Logs are basically the exponents of the power of 10. So if I say that we have 5 to the x equaling 125, if you want to solve for x, you're going to have to get that x out of the exponent. So what you do is you take the log of both sides. And what that does is it takes that x out of there, and you have the log of 5. X times the log of 5 equals the log of 125. And when you divide this over to the other side, you get x equals 3. Now, you're not going to have to do a tremendous amount of that, but the basic idea is that the log is referring to the exponent. So if you take 10 to the x and then you take the log of that, the log of 10 to the x is just going to be x. Just like, and if I scroll down just a little bit here, if I have 10 to the second power, if I take the log of 10 to the second power, that's going to give me 2. So, just a little quick review of logs. If it's been a while since you've done those, they're just referring to the exponent. So, here's the deal. If you have a pH that is less than 7, the solution will be acidic. If you have a pH that is greater than 7, the solution will be basic. And if you have a solution where the pH is equal to 7, then that solution is going to be neutral. Now, why is that? Well, let's just take a little stroll down. If you take a look at hydrogen concentrations and hydroxide concentrations, the two of them always have to equal 1 times 10 to the negative 14, kind of cramming it in there. 1 times 10 to the negative 14. So if I make a table, if hydrogen equals 10 to the negative 1, then hydroxide must equal 10 to the negative 13. If hydrogen equals 10 to the negative 2, hydroxide has to equal 10 to the negative 12. And so on and so forth. And continuing on down, what you'll find is that you have where hydrogen equals 10 to the negative 7 molar, hydroxide also equals 10 to the negative 7 molar. You knew that from previous podcasts. And if you continue on, you'll have hydrogen equals, say, 10 to the negative 12. Hydroxide will equal 10 to the negative 2, 10 to the negative 13, 10 to the negative 1. And so on and so forth. So when you multiply those always equal 10 to the negative 14. But what you'll find is, when you take the negative log of 10 to the negative 1, okay, the negative log of 10 to the negative 1, you're looking at the exponent. So if you have the log of that exponent, it's just a negative 1. But when you put this negative sign out here, that makes that a positive, because we just don't want to deal with negative numbers. So the pH of this solution would be 1, the pH solution of this solution would be 2, the pH of this solution would be 3, the pH of this solution would be 7, this would be 12, and this would be 13. So therefore, if the solution is less than 7, it's going to be acidic. Why? Because the hydrogen concentrations are greater at those points. If the pH is greater than 7, in all those cases, it's going to be basic. Why? Because the hydroxide would be in greater concentrations there. And if the pH is exactly at 7, the solution will be neutral. Why? Not because we just decided that 7 is a neutral pH, but because that is the pH at which both the hydrogen and the hydroxide concentrations are the same. Alright? So, now you know why pH of 7 is a neutral pH. In the next podcast, we're going to take a look at calculating the pHs of the example up above in example number 1. And we're also going to show you a shortcut way of calculating the acidity and basicity of various solutions. We'll see you next time.